Convolutional neural networks have revolutionized keyword spotting (KWS) technology, enabling smart devices to detect specific keywords in audio streams without physical contact. However, current small-footprint KWS models struggle in noisy environments, leading to false activations or missed detections. To address this, researchers have proposed FCA-Net, a novel convolutional neural network that combines mixer unit-based feature interaction with a two-dimensional convolution-based attention module. FCA-Net's attention module creates fine-grained attention weights to capture channel and frequency-specific information, boosting the model's ability to handle noisy conditions. This is achieved through a curriculum-based multi-condition training strategy, which progressively increases the difficulty of training samples, starting with easy, clean samples and then moving to difficult samples containing loud noise. The authors build upon previous work on KWS, including the use of deep neural networks, residual networks, and temporal convolutional neural networks. They also draw inspiration from curriculum learning, which has been proposed to augment noise robustness in acoustic models. Experimental results show that FCA-Net outperforms current state-of-the-art solutions for small-footprint KWS in noisy environments, making it reliable for real-world use. FCA-Net's design enables a small memory footprint while maintaining robustness in noisy environments. By leveraging mixer unit-based feature interaction and two-dimensional convolution-based attention, FCA-Net achieves improved performance over existing models. This breakthrough has significant implications for the development of reliable KWS systems, enabling smart devices to accurately detect keywords in real-world environments. Compact keyword spotting demands noise robustness in acoustic models, which traditional convolutional neural networks, CNNs, struggle to achieve. Attention mechanisms have been shown to improve performance, but integrating them into small-footprint keyword spotting systems remains a challenge. To address this, the authors propose a joint framework combining conv mixer blocks and attention mechanisms. The conv mixer architecture consists of preconvolutional, conv mixer, and postconvolutional blocks. The conv mixer block, a crucial component, integrates 2D and 1D depthwise separable convolutions and a mixer layer to enhance information flow. This is mathematically represented by the equations describing the conv mixer block, where input features are processed through convolution and activation functions. The joint framework leverages the strengths of both conv mixer blocks and attention mechanisms to improve noise robustness in compact keyword spotting. By combining these components, the authors aim to overcome the limitations of traditional CNNs and develop a more effective approach to small-footprint keyword spotting. The significance of this work lies in its potential to enhance the performance of keyword spotting systems in real-world environments, where noise and variability are inherent. By improving noise robustness, these systems can become more reliable and efficient, with applications in various fields, such as voice assistants, speech recognition, and hearing aids. The conv mixer module is a key component in the proposed model, consisting of three main parts: temporal domain features, processed features, and an output layer. The temporal domain features Y1 are derived from the input X through a 1D-DWS convolution function F2, followed by batch normalization and activation using the sigma function. Processed features Y2 are computed by applying another 1D-DWS convolution function F2 to Y1, with subsequent batch normalization and activation. The final output Y of the conv mixer module is obtained by summing the input X, intermediate features Y1, and processed features Y2. To enhance interaction between the feature space, the module utilizes two types of multi-layer perceptrons, MLPs, temporal channel mixing and frequency channel mixing. Each MLP mixing process involves two linear layers and a JELU activation unit, which operates on each temporal and frequency channel independently. The efficient attention module comprises three blocks: squeeze and excitation, SE, efficient channel attention, ECA, and convolution-based two-dimensional attention, C2D. The SE block applies global average pooling on the feature maps across the channel dimension, followed by two fully connected layers to assign importance weights to each channel. The ECA block uses global average pooling to aggregate features, then applies a 1D convolution with an adaptively determined kernel size to generate channel weights via a sigmoid function. The C2D block calculates fine-grained attention weights for various channel and frequency positions using convolution operations instead of fully connected layers. It first pools the input feature map along the time dimension using global average pooling, GAP, and then passes it through two consecutive 2D convolutional layers to compute the attention weights omega. These attention weights omega represent the importance of each channel frequency pair, and are used to reweight the output of each channel, emphasizing important features and suppressing less significant ones. The C2D block is a novel attention mechanism that calculates attention weights using convolution operations, requiring fewer parameters and less computational cost compared to fully connected layers. This mechanism generates more detailed and specific attention weights by simultaneously considering both channel and frequency dimensions, enhancing feature representation capability. The attention weights are applied to the original input feature map through elementwise multiplication, emphasizing important channel frequency pairs while suppressing less important ones. The proposed FCA-Net combines the conv mixer with the C2D attention mechanism for keyword spotting. The FCA-Net configuration adds C2D attention after each conv mixer block, while other variants, such as FCA-Net pre, FCA-Net post, and FCA-Net final, add C2D attention to specific parts of the network. An ablation study is set up to evaluate the different variants. The experiment setting uses the Google Speech Commands v2 dataset, which contains 105,000 utterances of 35 unique words, each 1 second long and sampled at 16 kHz. The dataset is divided into training, validation, and test sets for the 12 label classification task. To simulate a noisy farfield environment, noise samples from the MUSAN dataset are added to the command samples in 4 progressively harder steps, with noise levels increasing in decrements of 5 decibels. The implementation details involve using MEL frequency Kepstrel coefficients, MFCC, with specific parameters, and performing data augmentation with time shifts and spectrogram masking. The model is trained with a batch size of 128, an initial learning rate of 0.005, and a learning rate scheduler with cosine annealing warm restarts. The model is trained for 200 epochs with early stopping if there is no improvement for 20 epochs. The study also applies 3 augmentation methods: mix-up, spec-augment, and curriculum learning. Additionally, several state-of-the-art keyword spotting models are set up as baselines, including MH-Atran, KWT, AST-Tiny, BC-ResNet 6, and ResNet 15, to analyze the proposed model. The comparative study among state-of-the-art models for keyword spotting tasks under noisy conditions is presented. FCA-Net is compared with MH-Atran, KWT1, ResNet 15, MatchboxNet 6x2x64, BC-ResNet 6, conv mixer, AST-Tiny, and KWT3. FCA-Net demonstrates superior performance among small models, achieving up to 3% better accuracy than other models with similar memory footprints. It also shows a significant reduction in model parameters and max, indicating lower memory and computation resource requirements. Under challenging noisy conditions, FCA-Net outperforms other models by up to 7.4%, making it a reliable and efficient solution for real-world applications. The ablation study explores the impact of different attention modules and their positions on the performance of KWS systems in noisy environments. The results indicate that incorporating efficient attention modules significantly enhances the robustness of KWS systems. The C2D module demonstrates superior performance across various noise levels, especially when placed at all positions within the conv mixer block. This setup proves to be the most effective strategy for enhancing noise robustness, making the C2D module particularly valuable for improving KWS system performance in challenging auditory conditions. The proposed FCA-Net model combines mixer unit-based feature interaction with an efficient 2-dimensional convolution-based attention module, further strengthened by a curriculum-based multi-condition training strategy. The experimental results demonstrate that FCA-Net achieves state-of-the-art accuracy among small models and outperforms existing solutions in noisy conditions. Additionally, FCA-Net significantly reduces the number of parameters and computational resources required, making it both efficient and effective for real-world applications. This page provides an extensive list of research papers focusing on the development and application of advanced computational models in environmental science. These studies explore various aspects, including climate change, pollution, and conservation strategies, utilizing cutting-edge methodologies and technologies. The first set of papers delves into the realm of climate change, examining its impact on global ecosystems and human societies. These investigations employ sophisticated climate models to predict future trends, assess vulnerabilities, and evaluate potential mitigation strategies. Key findings highlight the importance of early intervention and the critical role of international cooperation in addressing this global challenge. A second group of studies investigates pollution, encompassing both traditional pollutants like CO2 and emerging contaminants such as microplastics. Researchers utilize statistical analysis, machine learning algorithms, and field experiments to understand the sources, pathways, and effects of these pollutants. Significant insights include the identification of novel pollution sources and the development of innovative remediation techniques. The third category of research centers around conservation strategies, with a particular emphasis on biodiversity preservation and sustainable resource management. These papers leverage spatial analysis, network theory, and game theory to devise effective conservation plans that balance human needs with environmental protection. Notable discoveries involve the creation of novel conservation frameworks and the demonstration of their efficacy in real-world scenarios. In conclusion, this compilation of research papers showcases the breadth and depth of computational models in environmental science, shedding light on pressing issues and proposing actionable solutions. It serves as a valuable resource for researchers, policymakers, and practitioners seeking to understand and address the complex environmental challenges facing our planet.